Okay, I would like to talk about this problem that I got wrong the first time I tried to do it. So first I'm going to explain why my method was wrong, and then I'm going to give an alternative method that's based on the density. I've been trying to emphasize that the density function tells you all the information there is about the random variables. So you can always do a problem using the density function. Just sometimes there may be some shortcuts. All right, so here first let me give the wrong approach. Okay, now before I approach, let me read the problem. Let x be a normal random variable, standard normal random variable, mean zero variance 1. Let y be 2x plus w, where w is also standard normal random variable and is independent of x. First, find the MMSE estimator of x given y. So that's the part I got wrong. So that's really the part I'm going to focus on. Right? So here's the wrong approach. Here it says I want to find x given y. So my approach was, this is solve for x, okay, and you get y minus w times 1/2 is equal to x. Okay, now we want x given y. Okay, so x given y means y is known. Okay, so let's just set capital Y equal to y. So henceforth, if we know y, then y should be treated as a specific value. Okay, so then here we would get 1/2 times y minus w is equal to x. Is equal to x. And what I said was that w is mean 0, variance 1. So if I take the expected value of the left-hand side, that's going to be equal to the expected value of y over 2 plus expected value of w over 2, which is equal to the expected value. Well, expected value of y over 2 is just y over 2. Okay, and this is plus 0. So my answer was this, because the MMSE estimator is the expected value. Now what's wrong with this is that when you know y, the y affects w. Okay? If you know something about y, you know something about w. Why is that? Because y depends on w. So the error is that w also depends on y. Okay. So what I should have done is something like this. I can do 1/2 y minus w is equal to x. I can do that, but then I have to condition on y on both sides. So I'd have to have 1/2 times y, and I'll condition this way, y equals y, minus w given y equals y is equal to x given y equals y. Now, I assume that w given y equals y was just w, but it's not. You can calculate the covariance of w and y, and it will certainly be non-zero because y is correlated with w. Okay. So this is not equal to w. Okay. So that means the previous argument is wrong. Right now, I could say, well, let's just compute w given y equals y, but that's just as difficult as computing x given y equals y to begin with. Okay, so let's do another correct approach. Now, you can use the formula in the book, but like I said, I prefer not to memorize formulas, but to understand what's going on. So let me repeat the, let me see, we want the correct argument. The correct argument. So let's go ahead and take this and copy it and do it again. Actually, I just want the first part, so I'm only going to copy the first part. Let me go ahead and copy that from my screen clipping here. So I only want this part. That's enough. I want more space on the screen. All right, here we go. Right now. All right, so x is n01, w is n01 is independent of x. So I want the joint distribution, or the joint density, of x and w. Okay, and that's just going to be f, the density function of x and w. Now both of them are normal 0, 1, so that's 1 over square root of 2 pi times e to the minus x squared. Now, since they're independent, I can multiply the density functions, and that's e to the minus w squared. Okay, so that's equal to 1 over 2 pi, because the two square roots come together, minus x squared minus w squared. Now, I want to find the estimator of x given y. And this is a distribution with x and w. So what I need to do is transform this to a distribution in x and w. Okay. So I want x given y. So that means I need to transform the density to be a density of x and y. Right. So in this case, you have to use the method of transformations. Fortunately, in the book, I was just looking at this, there is an example that's very similar to what we want to do. Here in this case, we have z equals 2x minus y, w equals minus x plus y, and we have x and y are two independent standard normal random variables, just like our x and w. And then you want to find f of zw. So let me see if I can copy this procedure and see if we can do something analogous to this case. I'm not sure how far down I can copy, but let's just start from here. Actually, let me zoom in so I can copy a little bit more. Okay. So I think this is actually enough. So let's take this. Got this. All right, so let me copy this, and we'll paste into our window, and we will see what we can do here. Remember, I want the joint distribution xy of fxy. I have the joint distribution with x and w. I need the joint distribution with x and y. All right, so let me insert my screen clipping. I think that's enough. And let's make it smaller so that we can fit it in and do something on the side while we're doing this. Get rid of it. Notice here. All right. So I'll just follow this step by step. All right. So again, we want to replace z and w with x and y. So let's do that. Right. So instead of z and w here, I have x. Now x in our case, x is just equal to x. And then y is equal to 2x plus w. Did I get that right? Better make sure. I actually did this video before, and I had to copy down the wrong equation. I had to redo the whole video. I think I may also have corrected these two. These were not correct before. Okay, so we have this. And then what do we want to do? So we have the joint distribution. So here we have the same thing. Here we have f of xw is equal to 1 over 2 pi, just the same thing we have now, exp of minus x squared plus w squared over 2. Now, we want to define the function g, where zw is a function of x and y. And here they've just translated this function with random variables into a function of ordinary variables. So in my case, I want to get xy, and that's just going to be equal to x and then 2x plus w. Okay. Now here we want to invert the function. Okay. Here they expressed z and w in terms of x and y. Now they want to express x and y in terms of z and w. So if we invert, we just get x equals x, and then we get w is equal to, let's see, y minus 2x. So this first one here is my h1. The second one here is my h2. Let me write that explicitly. h1, my new variables are x and y, and that's going to be x, and h2 of xy is equal to, well, let me write it this way, minus 2x plus 1. All right. Now I need to compute this Jacobian determinant. Well, what I do need here is this f of zw is equal to, so let's just write this down. Now, in my case, I want f of xy. And that's going to be fxy of x and y is equal to, now here I have fxw. I'm just changing the variables around. And then this is h1 of xy and h2 of xy times this Jacobian determinant, j. And my j is equal to the determinant. Well, let me just put this in here. Instead of this x, I'm going to have x. Instead of this w, I'm going to have y. I'm going to have x here and y here. And you can figure this out. Derivative of this with respect to x is 1. Derivative with respect to y is 0. Derivative of this with respect to x is minus 2. Derivative of this with respect to y is 1. So this is just equal to 1. That's nice. So what do we get in the end? fxy of x and y is equal to, now I have to plug these things in here. fxw, well, fxw was this. It was 1 over 2 pi. It's this number, it's this up here. So it's 1 over 2 pi times the exponential. Then the x stays the same because h1 is the same. So that's minus x squared plus, now in the second place I put h2. h2 is minus 2x plus y. This is all divided by 2. And then here I have closed bracket. And that's my new density. Okay. Now, what do I want? I want to find the conditional density. I'm sorry, I want to find the expectation of x given y equals y. Okay, that's equal to that's the MMSE estimator. So we could write that as an integral. That's equal to the integral of x times fxy of xy. Okay, in this case, y is known, so we just treat y as a constant. So that looks a little bit complicated. Let's try to do a simpler way. And I want to refashion this fxy, and I want to express it as a Gaussian in x. Because if I put this in Gaussian form, we can read the expected value of a Gaussian off of the Gaussian form, right? You know you have expectation of x minus mu squared. You have the exponential of x minus mu squared. In that case, mu is the expected value. So we want to re-express this so that we can read off the expected value. From the form of the distribution. Okay, so let's do that. So here we have in our exponent, we have minus, I'm sorry, this minus applies to both of these. So let me make that clear. Okay. We have exp of minus, and then we have x squared. Then let's write this out. If I take the minus 2x squared, so that's going to be plus 5, I'm sorry, plus 4 x squared. Then it's going to be minus, let's see, 4xy. And then we're going to have plus y squared. This is all over 2. All right. So let me complete the square. And then I'll get this as a nice form in x. Okay. I have x squared plus 4x squared. That's going to give me 5x squared. Then I have minus 4xy. Let me write the plus y squared out here. Now, in order to complete the square, we'll have to do something here. And this is still over 2. Okay. So let me write one more line. So I can write this as 5 halves times x squared. Then if I factor out a 5 here, this is going to be minus 4/5 xy. And then I'll leave this here, and I'll have a plus y squared over 2 out here still. Okay, now how do I complete the square here? Well, I want to have a term in y because I have my x squared term here. So that's going to be a plus 2y over 5 squared. Okay, and then to cancel that out, I'm going to have to subtract out here 5 halves times 2/5 over y squared. So that's going to give me just 2y squared over 5. So altogether, I get 5 halves, and then this is going to be x minus 2y over 5 squared. And then I have plus, and then I have to convert this to tenths, right? That's 5/10 minus 4/10, so that's y squared over 2. Now, let's plug this back into our exponent. Remember, we only took the positive part when we completed the square. So our exponent becomes exp to the minus, and then we have 5. I'm going to write this a different way. I'm going to write it as x minus 2y over 5 squared, and then I'm going to divide by over 2 times 1/5. And then this is going to be minus y squared over 2. All right, so my distribution, I can write my distribution this way. It's going to, what do I have in front? The 1 over 2 pi still. Yeah, 1 over 2 pi still doesn't change. So I have 1 over 2 pi times exp of minus x minus 2y over 5 squared over 2 times 1/5. This is minus y squared over 2. So what do we have here? We have a Gaussian that depends on x this way, plus a function of y, but y doesn't vary because we're treating y as a constant. So we can see that as x is varying, this is just like a Gaussian with center 2y over 5, that's the mean, x minus mu squared, and then the variance is 1/5. Okay. Now we can verify that if we want to find f of x given y, of x comma y, x given y. Remember how you take this? You take this distribution here, so it's going to be 1 over 2 pi times the exponent of minus x minus 2y over 5 squared over 2 times 1/5 times minus y squared over 2. And then you have to divide that by the integral over x. This is going to be this is fx. This is fxy. And then you have to divide by fy. And divide by the integral over x of 1 over 2 pi times exp of minus x minus 2y over 5 squared over 2 times over 2 over 2 times 1/5. And then here I'm going to write this separately times the exponent of minus y squared over 2. And that's dx. Now this is a constant, so this cancels what's on top. These parts simply cancel out. And the denominator simply becomes a constant. Why is that? Well, you can see that this part is Gaussian. All that the minus 2y over 5 does is shift it over. Right? So it's a shifted Gaussian that you're integrating over x. The y doesn't affect the value. So this whole entire bottom becomes a constant. So what do we have here? This is the density of x given y of x given y is the density. So in x, right? X is the variable that I'm having the density in. I'm treating y as a constant. So is a density with is the density of a Gaussian with mean. Well, the mean here is this minus 2y over 5, or 2y over 5. And variance, well, you can read the variance off down here, it's 1/5. Okay. So that means that the expected value of x given y equals y is equal to 2y over 5. Okay? Right. Now, this does seem like a long way to do it, but in fact, by doing it this way, we can pretty much complete the entire problem. Because if you look at the parts 2 and 3 of the problem, I'll try to go back there and complete those two parts. Well, actually, I have the problem at the top, don't I? Part B says find the MSE of this estimator. So it's the expected value of x minus xm, right? So that's just the variance of this Gaussian, okay? So B, I want the expected value of x minus xm squared. And again, this is what xm is. That's just equal to the variance of this distribution. Okay, and what's that? Well, it's 1/5. Okay, now part C was you wanted to show that expectation of x is the expectation of xm squared plus expectation of x twiddle. X twiddle is just this, is this here. This is x twiddle, the difference here. Okay, so if I want expectation of x squared, okay, so the question is that equal to expectation of xm squared plus expectation of x twiddle squared? Now this expectation of x twiddle squared, that's just equal to the 1/5. Okay. What about this one here? Well, xm was just 2y over 5. So this is the expectation of 2, but it's going to be 2 over 5y squared. So let's use our magic with expectations, all right? This expectation is equal to 2 over 5 squared, I can pull that out, times the expectation of y squared. Okay. Now, remember that this is, so y squared is equal to, what was it, 2x plus y, 2x plus w. Okay. Now, knowing that x and w are independent, that's going to get me expectation, well, I'll just write it out, 4x squared plus w squared plus 2x, or 4xy, xw. All right, now this expectation is going to be 0 because of independence. And let me not forget the 2/5 squared, so that's going to be 4 over 25. And then here I should put a 4 over 25 here. Okay. Now we know the expectation of x squared, that's just 1. We know the expectation of w squared, that's just 1 also. So that's equal to 4 over 25 times 4 plus 1. So that's 4 over 25 times 5, so that's 4 over 5. Okay, so we get 4 over 5 for the first value, and we get 1 over 5 for the second value. And that's equal to 1. It's equal to the expectation of x squared. And again, since x is a normal 0, 1 random variable, that's what the expectation of x squared is. All right, so we've completed the entire problem. Pretty much did all the problem just by doing this alternative way of finding part A. Okay, that's it. Thanks for watching.